Good morning, student. In this class, we are going to discuss about the longitudinal wave, the properties of longitudinal wave, the phase velocities, the energy and the intensity of the longitudinal wave. All these topics are in your syllabus. Therefore, I am going to discuss all these topics in this class. So, first, let's start with the propagation of a sound wave. As I have already told you, and the sound wave is a longitudinal wave because the vibration of the molecules are in the direction of the propagation of the sound. Here, the molecules mean the molecules or the collection of molecules through which the sound wave propagate. Actually, it's the molecules of the medium. For example, if the sound propagates through gaseous medium, so it's the constituent of that air or gaseous medium. Okay, so in this slide, on the top row, what you have seen, the in the steady state, the location of the molecules. Okay, I have shown the location of the molecule with using different kind of color dots. Okay, so in the steady state, the molecules are in steady position. Okay, when a longitudinal wave like sound wave propagate, then what happen? That say the wave is propagating in the x direction, so the displacement of the molecules from its equilibrium position will be in the x direction. As you can see, on the left hand side of the orange color dot, the molecules are uh, displaced from its original position towards right hand side, and on the right hand side of the orange color molecule, the all other molecules are displaced from its equilibrium position towards the left hand side. Okay, this is this is at certain instant of time. Okay, so the time is freeze here. And one can also notice the black color and the orange color dot, it does not displace from its equilibrium position because the molecule surrounding these two dots are displaced in equal amount from all the sides. For example, the displacement of the molecule in the left hand side of the orange color dot can be taken as positive, while the displacement of the molecule from the right hand side of the orange color dot can be taken as negative. Similarly, and the same logic applies to the black molecules also. All the molecules on the right hand side of the black molecule are displaced towards the uh, right hand side, and all the molecules in the left hand side are displaced towards the negative side. That is, if one is positive, then another will be negative. So these two molecules become steady. Okay, so what happens now if I represent the displacement towards the positive x-axis as the positive displacement, and displacement towards the negative x-axis as a negative displacement, then and if we plot the displacement from equilibrium position in the y-axis and as a function of x, then one can see this sinusoidal oscillation. Okay, this oscillation, the shape of the oscillation is similar for transverse wave, and also it is true for longitudinal wave. Okay, so here the different color represent the displacement from its equilibrium position. One thing you can notice from the slide that there is a accumulation of molecule around the orange color molecule, and and there is a absence of molecule around the black color molecules. Okay, so this phenomena of accumulation of molecule around a certain molecule is known as the compression, while the dispersion of the molecule around a certain molecule is known as the compression. So in this way, at this instant of time when the sound wave propagates, so there is a presence of a compression region which is surrounded by two rarefaction region. Okay, once this cycle is completed, then the compression region will be converted to the rarefaction region, and the rarefaction region will be converted to the compression region. In this way, the sound wave will travel through the medium. Okay, so sound wave basically, as I have already told in the first part of the video, that sound wave travel through a succession of compression and rarefaction, now you can understand how this success, how this compression and rarefaction region are formed when sound travels through a gaseous medium. Okay, I hope this slide is clear now. And next, I mean here I have shown the successive region of compression and rarefaction, as I told in the previous slide. The accumulation of molecule can be termed as the compression region, where the dispersion of molecule it can be termed as a rarefaction region. Now, since sound wave is the sound wave travel through the air medium, and the air has both pressure, volume, temperature, as well as density. So the thermodynamics of the gas or the air molecule we have to consider while studying the propagation of sound wave through such type of medium. Okay, as you can see in the compressive region, there is a accumulation of molecules. So the gas pressure at that regions will be much higher. Okay, so this positive pressure is shown by the positive cycle of the sinusoidal part, where in the absence of molecule the pressure will be less than the normal. So it's shown as a negative cycle in that sinusoidal plot, and in the slide it is represented by the letter R. So in this way the successive positive pressure and negative pressure region will be formed as the sound wave propagate through the medium. For that reason also, for this reason also, the sound wave is known as the pressure wave, because here the behavior of pressure is also periodic, just like a the amplitude or the energy or intensity of a wave. The behavior of pressure as the sound propagate through the medium is also periodic. Okay, that's why sound wave are sometimes called as the pressure wave. Now, one thing you can understand from the basic thermodynamics, since we know that if there is an increase of pressure, then it will automatically increase or decrease the temperature. Okay, so when a sound wave propagate through a gas medium, then this phenomena we cannot consider it as an isothermal process, because whenever there is an increase of pressure, there will be a change in temperature. So sound wave propagation is never been an isothermal process. Probably you have studied it in your class 11 textbook. When Newton derived his formula for sound propagation, he assumed that the propagation was isothermal. But in this course, we are not going to consider the isothermal propagation of sound through a medium, because we know that there is a existence of compression and rarefaction region, and due to that there will be local pressure gradient. That means the pressure will not be same through the medium, and as a result there will be a difference of temperature at different part of the medium. That's why the sound wave propagation through medium, we cannot consider it as a isothermal change. So whatever the thermodynamics we will do in the sound wave propagation, will basically consider this process to be a adiabatic process. Adiabatic because we'll assume that, this assumption is by and large true. We'll assume that during the propagation of the wave, there is no increase or decrease of energy of the wave. Energy doesn't dissipate. Okay, if energy does dissipate, then it may be possible that we cannot hear what other people speak. Okay, so we'll assume that the energy of the wave doesn't changes as it propagates. That means the sound wave doesn't exchange heat energy with the surrounding medium, and that's why for that purpose we'll assume that the propagation of sound wave through air medium is basically an adiabatic change. Okay, so remember this thing. The propagation of sound wave is known as the pressure wave, because the variation of pressure is periodic, and it is due to the periodic variation of compression and rarefaction region as the sound wave propagate through the medium. And secondly, this process is not isothermal, because there will be local temperature gradient as the sound wave propagate, and we'll assume that the process is adiabatic, because the sound wave does not lose this energy or intensity as it propagates through the medium. Okay, thank you.